A glass of wine or a cup of coffee is a chaotic liquid matrix. It is packed with volatile organic compounds, or VOCs, which are chemicals that easily evaporate into the air at room temperature. To make sense of this chaos, chemists rely on solid-phase microextraction, or SPME, and gas chromatography mass spectrometry, or GCMS. SPME is a technique that extracts trace chemicals from the air, while GCMS is an instrument that separates and identifies those specific individual molecules. These instruments operate with staggering precision. They can detect target markers like 3-sulfanyl hexane 1-ol, or 3SH, a compound responsible for tropical fruit aromas, or 4-ethyl guaiacol, or 4EG, a molecule that smells like smoke and clove. They can isolate these molecules even when they exist at concentrations of a few parts per trillion. Our own biology matches this mechanical precision. The human olfactory system can detect these exact same molecules at the identical parts per trillion threshold. But there is a glaring discrepancy between the two systems. If you expose a sensor to a chemical, it registers a constant signal. If you expose a human to that same chemical, our perception decays rapidly. While machines are static, passive receivers of chemical data, human olfaction is a dynamic, aggressively filtering neurological process. For decades, sensory professionals treated this decay as a mechanical failure. They assumed flavor fatigue was simply peripheral receptor burnout, meaning the physical sensors inside the nose were saturated and could no longer fire. A physiological concept known as the duality of smell proves that assumption is incorrect. The duality of smell refers to the two distinct routes air takes to reach our receptors. We perceive odorants orthonasally when we inhale them through the front of the nose, and retronasally when we exhale or swallow, pushing air up through the nasopharynx at the back of the throat. Sensory fatigue is actually a highly sophisticated, vector-dependent filtering mechanism orchestrated by the piriform cortex. The piriform cortex is the largest area of the human brain dedicated strictly to processing olfactory information. Researchers proved this by running clinical trials that bypass peripheral exhaustion entirely. They delivered the exact same chemical to the exact same physical receptors, but altered the aerodynamic direction the chemical arrived from. If fatigue is a physical saturation of the receptors, then continuous exposure should cause perception to drop to zero, regardless of the airflow direction. If the pathways yield different decay rates, the brain is actively filtering the data. This diagram traces the orthonasal airflow pathway. Air enters the nose, sweeping upward to hit the olfactory epithelium. Conversely, when exhaling, retronasal airflow rises from the back of the throat to strike that exact same patch of sensory neurons. Aerodynamic studies confirm these two distinct directional vectors do not physically interact or interfere. To map how the brain handles these vectors, researchers used a solution of phenylethyl alcohol, or PEA. PEA is a pure olfactory stimulant that smells like roses, strictly triggering smell receptors without activating pain nerves. They also tested a solution of N-butyl acetate, or BA. It smells like bananas, but acts as a mixed stimulant, triggering both the olfactory system and the trigeminal nerve, which detects irritation and physical sensations in the face. By pumping these specific chemical triggers through completely isolated aerodynamic vectors at a constant rate, researchers created a rigorous biological control. This setup allowed them to map exactly how fast neural fatigue sets in. This graph charts the experiment, plotting time against odor intensity on a 0 to 10 visual analog scale. For the PEA odorant, perception drops sharply in the first few minutes, then shallows out into a slow, gradual decline. Eventually, subjects hit full habituation, registering absolutely zero perception, despite a constant chemical stream. The data reveals a critical divergence. Perception degrades significantly faster when inhaled through the front of the nose compared to when exhaled from the back of the throat. The median duration to reach full habituation for orthonasal was 377 seconds versus 416 seconds for retronasal. The ratings show a significant gap, specifically at the 1-minute and 4-minute markers. The chemical concentration arriving at the receptors is identical in both scenarios. This temporal gap in perception proves the central nervous system applies completely different degradation algorithms based strictly on the airflow's directional vector. At the experiment's critical moment, continuous orthonasal stimulation drops until it hits 0 on the intensity scale. The subject can no longer smell the odor. But the instant the gas flow is routed to the retronasal pathway, perception spikes vertically back to 3.9. If the peripheral receptors were physically saturated with the chemical, changing the airflow direction would yield a 0 response. The receptors would be full. This instantaneous rebound renders the peripheral burnout theory biologically impossible. This microscopic view shows the olfactory epithelium divided into a grid of distinct spatial expression zones. Front-to-back orthonasal airflow hits the front zones a fraction of a millisecond before the back. Conversely, retronasal airflow hits the back receptor zones first. The olfactory bulb processes these minute directional temporal shifts and translates them into a highly organized, stereotyped information map. Even though the chemical is the same and the exact same receptors are firing, the sequence of the firing is reversed. This altered spatial temporal coding tricks the pyriform cortex into registering the identical chemical signature as a completely new signal. This phenomenon is called incomplete cross-habituation. It definitively isolates the central nervous system, specifically the pyriform cortex, as an active spatial temporal chemical filter. On the left, a static gas chromatograph maps a wine matrix. On the right, a dynamic heat map of the pyriform cortex aggressively suppresses stable background odorants. This deliberate muting instantly highlights transient anomalies, like a sudden spike in 4-EP, a barnyard-smelling compound. This filtering system is also calibrated for threat detection. When subjects were tested with the BA compound, a mixed trigeminal nerve stimulant, they exhibited a significantly stronger cross-habituation response than they did with the pure PEA odorant. The central nervous system is hardwired to prioritize and resist habituating to trigeminal irritants because sensations like burning or stinging signal potential environmental hazards. Sensory fatigue is not a biological flaw or a hindrance to professionals evaluating wine or food. It is a highly evolved survival mechanism designed specifically to parse complex chemical environments. By understanding this mechanism, sensory professionals can intentionally weaponize individuality at smell. When evaluating a beverage, alternating between short orthonasal sniffs and long retronasal exhalations forces the air across the epithelium in opposite directions. By constantly switching their evaluation vectors, experts can intentionally bypass their own cortical filters. They're effectively resetting their spatio-temporal neural maps in real time, allowing them to evaluate complex chemical matrices with entirely renewed precision.